Hi everybody, welcome to NE 630, Introduction to Nuclear Reactor Physics. My name is Ali Abdu and I am a professor at the Nuclear Engineering Department. So let me first give you my contact information in case you want to contact me. So this is my first name, my second name, and I am at 137 the Ward Hall. If you cannot find me at 137, most probably I am at 142 also Ward Hall. This is my lab, and you can contact Muhammad at the end of the office here or class. He's my student. He will know where I am, so you can contact him anytime. Also, you can email me at aeabdou@ksu.edu. In case you want my office phone number, 785-532-7182. So again, this is, as I just stated, Nuclear Reactor Theory course. The course will be meeting here Monday, Wednesday, Friday from 1:30 to 2:20. And for the office hours, usually, can you share this one until I finish this one and I will give it to you. So the office hour, usually I have for this semester, I have the office hour open. So whenever you need any help, just stop by my office and I will be more than happy to help. If I am busy and you have, for example, time to come back, I will ask you to come back. If it is urgent, I will put my things aside and try to help you. The textbook for the course is Stacy, and this is what we taught last semester. It's a nuclear reactor physics. It is 2 parts. The first one is for this class, so we will be studying chapters. Part 1, the neutron nuclear reaction, neutron chain fission reaction, the neutron diffusion theory, the neutron energy distribution, the nuclear reactor dynamics, the fuel burn-up, and all the types of nuclear power reactors. If we have time before the end of the semester, we will just visit the reactor safety. Last year, we did not discuss the reactor safety. The second part is the advanced reactor physics, and I think all of you are nuclear engineering majors, yes, or option. So I think if you take the neutronic class with Dr. Bill Don, he will be able to figure out the second part, although he does not teach it from this book. For further or optional reading, if you are interested, what I noticed from the Stacy book that he grabbed parts from different books and compile his book. So mainly he uses Lamarche, Introduction to Nuclear Reactor Theory, and I give it to you here in the syllabus. Lamarche Reactor Theory is a very excellent book. I studied this one when I was like you, undergrad. And the beauty of Lamarche is it is physics oriented. So if you want to understand the physics, it is physics oriented. There is Henry. And Henry is a little bit more advanced and also a little bit difficult, because Henry is mathematically advanced or mathematically oriented. It's different from Lamarche. Lamarche treats the problem from the physics point of view, although it has mathematics. But Henry, the mathematics is more solid and more rigid. In between, and it's very, very nice to read, it's a very readable book, is Doderstadt and Hamilton, Nuclear Reactor Analysis, and this is one of the books that I find that it puts more focus in how the reactor is designed. It has chapter in the transport theory, neutron transfer theory, and so on. It's a very, very readable book and very nice book. So I like it the best over the 3 books. So you have it. You can search the library here and check out the book, for example. So during this semester, we will have 4 homeworks. The 4 homeworks will count for 40% toward your grade. So 4 10% each. We will have a midterm maybe after 2 months from now or so. We'll have the midterm. I did not decide yet the date. It will count for 20%. The final exam will count for 30%, and there is a 10% that will count for the participation in the class. So hopefully nobody will lose the 10%. Everybody will get the 10%. So last year, for example, I have I think I have 12 or 13 people or something, student in the class. Nobody got C except one, and he did horrible. So hopefully nobody will get C. Hopefully, just you will earn the grade. I did not give you grades. You will earn the grade. So try to help me, and I will be more than happy to help, of course, in the course. You will see that I put here underlined statement with red and bold. Note that the homework problems may be assigned from outside the book, because usually, again, I did not only focus in this book. Usually I wrote my lectures from this book, Duderstadt, Henry, Lamarche, and also there is another book which is just a very easy book, but it brings stuff from air. So which is Fundamental of Reactor Physics by Lewis. If you are interested in this book, it's Fundamentals of Reactor Physics, and the author is Lewis. So this is a very concise book. The whole book is almost 200 pages, 230 pages. So it's very good if you understand the physics here and you want to review before the exam date or something like this. You can go and read it. But the problem is sometimes it gives you some definition and that's it. There is no any mathematical derivation or anything like this. You do not know where he brought this, for example, formula or something like this. So it's better to focus on the lecture notes, of course, or the lectures, and also the book here, and try to hover around the 4 textbook that I give it to you. Again, I just talked to you about the chapters that we will be studying during this semester. One of the very important thing is the academic misconduct. You are more than welcome to work the homework together, but you are not allowed to copy each other homework. Last year, there's 2 students who came, and I noticed that they copy and paste, although they change the wording. So the wording was different, but the steps for solution is exactly the same. And when I asked them to meet me in the office after the first homework was turned on, and I asked both of them that this is plagiarizing, and I will not tolerate it, and I told them that why you did this, and one of them, he said, oh, it's not plagiarizing, I did not do it, and then I show them the 2 copies, and I say, okay, I do not care about wording, here is the steps, although he something like omitted a couple of symbols and stuff like this. And finally I say, well, I was busy, and I was out of town, and I was sick, and then he advised to help and stuff like this. Then I said, okay, if you are sick, please come and tell me, and I will be more than happy to extend the homework return date for you if you are sick. If there is, for example, something like out of your hands, I am not here to torture anybody. I am here to help you understand the material, and if I did not accomplish this goal, this means that I am not successful. So just stop by my office and tell me openly, Dr. Abdo, I have a problem, and I will be more than happy to help all of you. But please, if you have anything like this, please, more than welcome to work all together, but you are not welcome to copy each other homework. So this is this one. If you visited K-State Online, those lectures are videotaped for the Big 12 students, so you are more than welcome. Also, all of you have access to the K-State Online. So this lecture will be videotaped, and you can just review the lecture again, watch the videos, and see if you have any comments or anything like this. I will welcome your visit to my office. There is hands out that I put in the K-State Online for mathematical cheat sheets. So you can look at those mathematical cheat sheets. I try to help you, so I put everything that you will need in your undergrad, even not in this course, but anything in the College of Engineering. So you will find anything in advanced engineering mathematics, like solving differential equation, vector analysis, integral transform, special functions. You'll find stuff like algebra, stuff like geometry, everything you need. I put it in a PDF files. You are more than welcome to download it to your computer and use it, although it's not mine. So if you want to distribute it or anything like this, look for the author and then contact him for distribution. But for your own personal use, I already contacted the authors and I take permission to put the stuff online. So that's it for today. So just a quick introduction before we go to the course itself. This course is not meant to be a design course for nuclear reactors. And when I was like you in undergrad, I studied Lamarche, the whole book. And then I participated in the design of our nuclear reactor in Egypt, and I went to Argentina. And at this time, I went to the company, and they start talking to me about joining the department, the nuclear core design department. Then they start talking about cell calculation and core calculation and stuff like this, and I have no clue what they are talking about, although I studied Lamarche. So this is not a design course. But in order to understand the course itself, it will be better if we will talk briefly about how nuclear reactors are designed and stuff like this, so that you will appreciate, okay, why I'm studying this and why I'm taking this and that. So it will be verbally. I'm not going to discuss anything because it will be very extremely complicated. So if you look at the book, the first chapter is usually about cross sections and nuclear reactions and stuff like this. So neutron nuclear reactions. So why we need to know the neutron nuclear reactions? Very simple, because if we want to design a nuclear reactor, there is two major equations will be utilized in designing nuclear reactions. The first one, usually people will use what they call transport equation. If they want to do a simple calculation or something like this, or a subset for the transport codes, usually they use what they call diffusion codes. So whether you will use transport equation or diffusion equation, we are not going to discuss the transport equation during this course. It's in the higher level course. But most probably we will encounter the derivation of the diffusion equation. Maybe we will solve the one group diffusion equation and so on. In order to solve the diffusion equation will have terms. It's just diffusion equation is just an equation, continuity equation. And all of you know what is the continuity equation. So continuity equation, let's say that you have any physical property of interest. Let's say the physical property is L. And you want to know how this property changes. So you have what we call continuity equation. So we'll say, let's take a control volume and look for this L here. And then we'll say that the time rate of change of this property inside this control volume will be equal to what gets in that feeds this and what gets out. So it will, let's say that I have the N is, let's say, L dot inlet, and what gets out is L dot outlet. So it will be L dot inlet minus L dot outlet. What's this? So this is how you feed this quantity, by just injecting the quantity with time into the control volume. Then the quantity capital L decreases because part of it leaves the control volume. And then you will add any generation of this quantity inside the control volume. So let's take, for example, talk about something like, we are talking about a chemical reaction that produces something inside the control volume. So if the chemical reaction produces water, so there is water production because of, let's say, a chemical reaction. And you have a destruction term, let's call it D. So you have Q dot and D dot inside. So this is just a continuity equation. So the neutron transport equation is exactly the same. A transport equation that describes how the neutrons are conserved inside the reactor system. So the neutrons are conserved inside the reactor system. The time rate of change of total number of neutrons or the flux inside the nuclear reactor is equal to those two terms. We call them the leakage term. So here is the volume of the reactor, and there is neutrons getting out from the reactor surface. So this is called the leakage term. So usually we will denote this as divergence of the current, and we will know all those terminology later on in the course. Then we will have a production. What do you think? How the neutrons will be produced inside the nuclear reactor core?
Through fission.
Through fission, yes? So you will have a term here that will have something like this. Sigma fission multiplied by the flux. And this equation, by the way, is per unit volume. If you have a continuity equation, it will be per unit volume. So this is the production rate inside the nuclear reactor. Then there is a destruction rate. Where do you think the neutrons will go? Other than leakage, will be absorbed. So we will have here minus sigma absorption phi. And sigma absorption phi is the total number of neutrons absorbed per unit volume per second inside the volume of the reactor. Then what else? What do you think? We have already the fission. Do you think we have sources or sinks other than the fission and the absorption?
Delayed neutron.
It is included in the fission. We will talk about it in details during the course. What else do you think? The decay, it's very, yeah, it's included here also. But what do you think? If we have what we call external or extraneous neutron source. Nuclear reactors, so you will have here external source. If you want to start the nuclear reactor, for example, you will notice that at the very early beginning of the core, you need some seed neutrons so that the reactor will start. And then once the neutrons emitted from the source and it will encounter the nuclei, it will start the fission process. Then you will have the sustaining nuclear reaction, the chain reaction. Yes? So you need this source. Usually in the trigger reactor here at the K-State, we have a external source that's inside or outside the core to feed those neutrons. In our reactor, when I was working in the reactor in Egypt, we put the extraneous source at the very early beginning, then we removed it and we no longer need it because, as you said, the fission products will produce gamma rays. And around the nuclear core, we have what we call reflector. Our reflector, the reflector here was made of carbon or graphite. The reflector in Egypt reactor was made of beryllium. And beryllium has a very good property. It has a nuclear reaction called photoneutron reactions. So gamma rays will hit the beryllium and it will liberate one of the neutrons from the nuclei of the beryllium. So this works as an extraneous source for us. So we do not need to put any extraneous source inside the reactor after the first startup. So this is one of the things that you can think about. So this is the reactor equation. So as you see here, the reactor equation will have lots of parameters. So this is d phi by dt, and you'll have 1 over the velocity. So let's ignore the flux a little bit. What do you think? You have what? Lots of parameters. We'll have cross sections and stuff like this. Yes? So this is why we need to understand how the neutron interact with matter. And this is the first chapter. why we want to understand the nuclear reactions. Why? Because we need the nuclear reactions to understand it, then to experimentally evaluate the values of what? Of the cross sections, because the cross sections later on will be used in the diffusion equation or the transport equation. So if you look at chapter number 1, which is the basic reactor physics, the neutron nuclear reactions, you will notice that this chapter will talk about the nuclear reaction. The second chapter will talk more specifically about the fission process and how the fission take place and the cross section and all the parameters involved in the fission itself. Then, when you will do the solution or perform the solution for this equation, usually the transport equation is very complex or very complicated equation. So there is a problem. We cannot just solve it analytically, except for very special cases. So we need to solve it using computers. So we need to have numerical analysis techniques to solve the diffusion equation or the transport equation. If you want to do this, so you have to have initial values for parameters like the flux. So if you want to understand what's the initial value of the flux, you have to know how the flux look like inside a nuclear reactor. Yes? So usually, if we are talking about a nuclear reactor, the neutrons will induce fission. What do you think? What's the average energy, average neutron energy for the neutrons emitted from the fission? Do you have any idea?
200 MeV.
No, the 200 MeV is the total energy released per fission, but the neutrons will carry energy. Do you remember the average energy?
Is around 2 MeV.
Yeah, 1.98 MeV. The most probable is 0.7 MeV. So if you look for the distribution for the neutron, let's say that the y-axis will be the distribution function, and the x-axis will be the energy. So this is, we will call it f of E, where f of E gives me the number of neutrons carrying energy between E and E plus delta E. So if we look at this distribution function, and we look way here in the fission energy range, we will notice that we will have something like a distribution like this. We will visit this in details. So this is the distribution of the neutrons emitted from the fission, for example. This distribution is called chi of E. Okay? Chi of E. Then when the neutrons are emitted from the fission, what they will do? They will encounter the two types of nuclei. The first one are the fuel nuclei, and then the second one, if they escape fuel, they will encounter the moderator nuclei, which is water. So what they will happen, what they will do with the nuclei, they will have multiple knocks, yes, until they will be thermalized. So when they have this process, we call it neutron moderation. So you are moderating the energy of the neutrons. So you will notice that the neutrons will decrease. The number of neutrons with energies, let's say, from the fission and below, will be doing something like this. And then once the neutrons will be moderated and they have energies, let's say, above the thermal energy of water, which is, let's say, if the water is at 300 degree Kelvin or something like this, or 290 something, this means that the energy is around, this is the temperature, the energy is around 0.025, 25 milli electron volts. They will start thermalizing their energy with the nuclei or atoms of the medium. What do we mean by thermalizing? So they will reach to the moment that the energy taken from the water molecules or water atoms is exactly equal to the energy given to the water molecule. So there is no net no net exchange. They have the similar energy like the water, and in this case they will have a distribution called Maxwellian distribution. So this is called the Maxwellian distribution, and this is called 1 over E distribution. How did we know this? So we will know this by studying the chapter number 4, the neutron energy distribution. Okay, so we'll study chapter number 4, and this will give us how the neutron behaves in the fission energy region, in the thermalization or moderation energy region. This is called, by the way, epithermal region. And this is fast region, and this is thermal region. So usually, for you to remember, the thermal region starts from anywhere very, very low energy up to nearly 1 electron volt. And the epithermal starts from 1 electron volt up to 100,000 electron volts. And then the fast region, which is the fission region, will start from anywhere from 100,000. There is neutrons reported to get out of fission up to 10 million electron volt, but this is a very rare number of neutrons. But let's say up to 5 MeV or so will be the upper limit, 5, 10 MeV, something like this. So now, if we knew by studying chapter number 4, the neutron energy distribution, once we study this chapter, we'll be able to figure out this distribution, how we get it, and so on. We will be using, in higher courses, we will be using this flux distribution to give an initial guess, for example, to calculate stuff like cross-section, average cross-section over energy grooves and stuff like this. So this is this part. Chapter number 3 will be mainly about neutron diffusion theory, and we will be driving the diffusion equation in this chapter. So this is called, if we neglect the time rate of change term, it's called the steady state. So you have an equilibrium between production and losses in your system. So this is not the case. If the reactor is running in a steady state mode and the power is constant, usually this is the case. But let's say during the startup or during transitions or during shutdown or during power change modes or stuff like this, you are no longer in a steady state mode. You are in a transition mode, and you have to look for the solution for the time rate of change. Further on the course, we will look at the classification of nuclear reactors from the neutronic point of view, and then we will be able to figure out that there is 2 types of nuclear reactors. One is called neutronically tightly coupled core and neutronically loosely coupled core, and then once we differentiate between both, we'll be able to derive the point kinetic equation. And this point kinetic equation, we will assume that the reactor, the function for the flux can be decomposed to 2 separate functions multiplied by each other. One is a time dependent, the other one is a spatial dependent. And we will say that the spatial dependent function, which is the shape of the flux inside the reactor core, let's say we have a cylinder. So inside the cylinder or cylindrical core, the flux will be sinusoidal in the z direction. It will be Bessel function in the radial direction. We will study this in details. So we will assume that the shape does not change for the point kinetic equation, but what changes is how the flux will vary with time. The shape will be like this, but might be increasing as the power increase or decreasing as the power decrease, and then we will solve the reactor as if it is a point in space. So this is what we call the point diffusion equation. So this will be chapter number 5, the nuclear reactor dynamics. Of course, when you run the reactor for long enough time, for the point kinetic calculation, when you do small calculation, something like a day or two, you assume that you did not burn your fuel, for example, inside the nuclear reactor. But for long operation, something like months or years or something like this, you will notice that the fuel is depleted. So you have to take into consideration the depletion of the fuel, and also there is a buildup of fission products that will affect the performance and operation of your reactor, like what we call poisons, like samarium and xenon, and those will affect the operation of the nuclear reactor. We will study this in detail. So this will be the fuel burn-up, and then we'll conclude with the different types of nuclear reactors. So I give you some sort of roadmap of the course, because last year people complain, okay, I don't understand why we study this. Did you understand? Oh, I understand, but you know what? I do not know why you are doing all this work and all this mathematics and stuff, the stuff that you are doing in the blackboard, for example. So now, just imagine this is like a complete analysis now. We are preparing you to understand the different physical processes taking place inside the nuclear reactor. Then the next step is to get into the advanced courses for neutronics, let's say for radiation transport, calculation, and once you will do your future, let's say, graduate research work, you will get to know the reactor design codes and reactor design calculation. So this is just the introduction for this one here. So let's start now the first chapter. And our first chapter will be Muhammad, can you please turn on which one? This one? Did you see now? You can turn on the one on your side if you want. Yeah. Oh no, the other one? Yes. Thank you. So we'll study the first chapter here. So before getting into the details of the neutron nuclear interaction, I have to remind you some of the basic elements of nuclear physics or atomic physics that you studied last year or the year before in the NE 495. So let's start with the definition of the stable nuclei. So the nucleus, the atomic nucleus, is composed of particles, protons and neutrons. And what holds the nucleus tight is the nuclear forces. And those nuclear forces will have the domain of the nucleus itself. So way outside the nucleus, the nuclear forces drop to zero. So there is no existence for the nuclear forces outside the nucleus. So the range of the nuclear forces will be just, let's say, the radius of the nucleus itself. And if you look at the equation that represents the atomic or the nuclear radii versus the atomic number, this is the relation here. So 1.25 multiplied by 10 to the power of minus 13 a to the power of 1/3. And it's very easy to derive this equation. Just you will say that, okay, the number of nucleons inside the nucleus, which is number of neutrons and protons, will vary with the volume of the nucleus. And what is the volume of the nucleus? It's 4/3 if you consider the nucleus as a sphere. 4/3 multiplied by pi r cubed. So if you inverse the equation, you will notice that r is equal to some constant multiplied by a to the power of 1/3. And this constant happens to be the 1.25 multiplied by 10 to the power of minus 13. So it's a very direct representation here. So if we look at the stability curve, what do we mean by stability curve? So if we try to represent, for example, the number of protons, if we will collect all the known isotopes in the universe, and then have the y-axis as the number of protons in each one of those isotopes, and the x-axis as the number of neutrons inside the isotope. Then we will say, okay, hydrogen. How many protons inside hydrogen? 1. Is there any neutrons? No. So you will put it here. So 0 for the number of neutrons and 1 for the number of protons. Then deuterium, 1, 2. So you have 1 neutron, so it will be 1, 1. Okay? And so on. And you start putting those isotopes in the graph here for N versus Z. You will notice that we will construct this plot here, which we will call it the stability or the stable and unstable nuclide. Of course, you will notice that we have unstable nuclei and we have stable nuclei. How we will define stable and unstable nuclei? So scientists look at what they call the N over Z ratio, or sometimes they call it N over P ratio. N, where N is the total number of neutrons inside the nucleus, and Z or P is the total number of protons inside the nucleus. So if you look at this ratio and represent it here, if N is equal to P or Z here, this will give you a straight line, 45-degree slope. So we will notice that for small isotopes, small isotopes or atoms, the ratio is nearly 1. So if you look at oxygen 16, what's Z for oxygen 16? Is 8. 16, so 8 proton, 8 neutrons. So the number is 1 to 1. Magnesium 24, you will find that magnesium is what? If you divide by 2, it will be 12. So 12 over 12. If you look at silicon 14, so 14 over 14 is 1. And if you look at calcium, is what? It's 20 over 20 is also 1. Then once you move a little bit beyond the smaller or light nuclei, you will notice that you will deviate from the 1-to-1 ratio line. So you will deviate from this line. You will notice here is the line, and then the stability curve will be skewed towards the N here. So I have two representations. One of those is N is the x-axis, Z is the y-axis. The other one, N is the y-axis and Z is the x-axis. So you will find those two flavors usually in the literature. Sometimes people will represent it like this or like this. It does not matter. So you will see this skewness or the curvature of the curve is toward what? Toward the higher number of neutrons. Why? Why do you think when the atomic mass number increases, in order for a nucleus to be stable, you need more neutrons?
You must give up mass for binding energy.
Yes, because inside the nucleus you will have what? Protons. And the protons are charged positively. So they will start repelling each other. Yes? So in order to overcome this repulsive force between the protons inside the nucleus, you have to have something that does not, or some particle that does not depend on the charge. And always, all the time, they will have attraction between themselves. And what's this particle? Is the neutron. Because the neutrons does not have any charge, so they will attract each other and they will hold the nucleus together. This is why you need more neutrons to compensate for the repulsive force between the protons. And this is what you will see here. So you will notice that once we go up the curve, this ratio is no longer 1-to-1. This is the 1-to-1 curve here, but the ratio for the stability line will go something like 1.3 or so. So the most logical explanation, as I just stated, is the neutrons, they are neutrals and they do not repel each other, and you need those neutrons in order to overcome the repulsive force. So now let's proceed and discuss the binding energy. What do we mean by binding energy? So the binding energy, if we assume that we can construct the atom, for example, and we visited the atom workshop and we start looking for the shelves, and we said, okay, we want to construct the oxygen atom, which is 816. So I asked you to go to the for example, the drawer where the protons are, and I asked you to buy 8 protons, and then you will get another 8 neutrons, and then you will bring the 8 protons and 8 neutrons, and before you put the glue between them and form the atom, I asked you to weight the protons alone, the neutrons alone. Then you add the masses of all the protons and neutrons together. Then you weighted all the mass of the protons and neutrons, which they are separate now, and then you construct your atom, you squeeze everything together until you feel heat in your hands, and then you weighted the atom after you finish performing the process, for example. What you will discover is the mass of the constructed atom that you just constructed is less than the mass of the constituents. Where is the difference? Where it went? So this difference is the binding energy. It transformed it from mass to energy to hold the constituents of the nucleus together and to keep the nucleus tight. So this is what we call the binding energy. Again, if we get all the isotopes in the universe and then look at the mass number A, which is this one, and we put the mass number in the x-axis, okay? And we do this construction, thought construction experiment, and start looking for one by one for each of the isotopes and measure the binding energy. But we will not just measure the binding energy, but we will measure the total binding energy, then we will divide by the total number of nucleons inside the nucleus to get the average binding energy per particle. And this is what we call the binding energy per particle. So if we do this, we will construct this binding energy curve. And this binding energy curve have very nice properties. What are the nice properties? We will notice that it has a maximum here around steel or iron, around iron here, let's say iron and nickel and those isotopes. Then start decreasing. So if you come to the very heavy elements, like uranium-235, for example, if you try to hit the uranium-235 with X and split uranium-235, what will happen? If you split the uranium-235 into 2 equal pieces, most probably it will be somewhere around here. Yes? Because the atomic mass number, if you divide 238 by 2, this will give you what? 1 and 38 is 19, 119 maybe? 119, 120. So 119, 120 will be here. What do you think? Here versus here. The binding energy is lower or higher? Higher. So you split a single atom with a lower binding energy and you produce 2 stable nuclei, because when the binding energy is high, the nucleus is more stable. So you produce 2 more stable nuclei here. So where is the difference of the binding energy will go? It will be released as energy for the forming particle or the particle that you form. And of course, this process is called fission. So if you have a neutron that hit the uranium-235, the neutron will act like the X. And then it will split the nucleus here, produce 2 here. You will have 2 fission fragments and a neutron. And the energy difference, the binding energy difference, will be carried by those 3 constituents. But because the neutron is very small mass and it is chargeless, it will escape from the site where it is generated in the fission and will leave the whole fuel to the moderator and then moderate and thermalize and then induce another nuclear reaction and so on. But for the fission fragments, they will still in the same location, more or less in the crystal lattice of the fuel. Maybe they will move a little bit, something like micron or so, but they will jiggle around and then finally come to stop. So the total energy produced per fission, this is what you just mentioned, which is the 200 million electron volts, it will be distributed among the 3 constituents and also among the gamma rays, and there is neutrinos involved, and neutrinos, they are massless, chargeless, they will escape from the whole reactor. So this is the fission process. In reverse of this process, there's another exciting process which is of similar beauty to the first process, and this is what we call nuclear fusion. So you can fuse particles from here or isotopes from here to form a higher mass number isotope here, and this is low binding energy isotopes, and you form a higher binding energy isotopes, and then you will produce this difference will be given as energy to the neutrons. This process is called fusion process, and a representative here for the fusion process, if you have the second isotope of hydrogen, which we call deuterons. So this is deuterium, and the particle of deuterium is called deuterons. So deuteron, usually we call it D-D reaction. So D hits D and then produce helium-3 and neutrons, and there is 17.6 million electron volt involved. So this 17.6 million electron volts, 3.5 million electron volt or 3.6 million electron volt will be given to the helium alpha particle, and 14.6 million electron volt will be given to the neutron. And this is the nuclear reaction that's responsible for producing energy in 99% of the universe. So this is the nuclear reaction that took place in sun. This is the nuclear reaction that took place in all the stars. And this is the goal of humanity, to substitute for energy through nuclear fusion. And if you look at ITER, www.iter.org, this is the International Thermonuclear Experimental Reactor being built in Cabarrach in France to achieve this goal of harnessing the nuclear fusion energy for humanity. So did you understand this one? Did you have any questions? Let's move on and give you some hints about the stability and the so the minimum energy needed if you want to induce a nuclear fission. So the minimum energy needed to induce a nuclear fission is called threshold energy. So you have to give this energy to the nucleus in order to induce the fission, and this is the threshold energy. So the threshold energy is very high if the number of protons is less than 90. For anything less than 90, so let's just go one time here back. So if you are here up to here, let's say krypton and maybe 90 is here. Anywhere here, if you want to split any of those nuclei, they have very high binding energy. So they are very tightly bound. In order to fission them, in order to split them, you have to give very high energy. And this is why, because they are with a high binding energy. Now, if Z is bigger than 90, usually for even mass number, you need 4 to 5 MeV. But for odd mass number, you need very low energy. And this is what we will discuss here in the next slide. So for certain nuclides like Volatile'i'M-240 and Californium-252, they exhibit a significant spontaneous fission. So without anything, without any touch from anywhere, you will find that the nucleus will say, oh, I have excessive energy inside me, so I will just split to release some energy, and it will produce a neutron. And this is the californium. This californium here is being used in nuclear industry as a neutron source. So sometimes you will hear the terminology that, okay, we have a californium source here that produce such and such with this activity, and And the production is coming from what? It's coming from the spontaneous fission. Okay, did you understand this? So now, if we proceed, let's define a couple of terminology here before we go into the details. We will define what we call fissile material, fissionable material, and fertile material. So what does it mean? Fissile material. So the fissile material is any material that induce fission, and not only induce fission. So it will induce it, and it will also sustain it. So it will keep the fission going on. So it will induce the fission, it will sustain it, a nuclear reaction at low energy. Some example of those isotopes are the uranium-233, 235, plutonium-239, and plutonium-241. If we look back at the previous slide, we will notice that for a Z greater than 90, 233, 235 is greater, 92 is greater than 90, yes? So 233, 235, 241, 239, is it Z, is it A even or odd? So this is why we said this slide is very low for odd nuclides. So for odd nuclides, we'll notice that this is odd. The nuclei will fission if you have a neutron just sitting next to the nucleus. So even with zero thermal energy, of course, there is nothing called zero, but for uranium-235, in order to induce the fission, you need 25 milli electron volt, which is very, very low. So whenever you have a 25 milli electron volt neutron sitting next to the nucleus, it will have a very good appetite, take it inside, and then split. So this is why you'll see that it is a fissile material. Fissionable material, those are the material that can undergo fission, but usually at higher energy. But they cannot sustain the nuclear chain reaction. And those are the even A nuclei that we talk about them. So all of them are above 90, as we just described in the last slide, and all of them are even A. So if you have even A and above 90, usually you need a threshold energy, high threshold energy, in order to induce the fission. And one of the example is the uranium-238. Of course, all of you know that the uranium that exists in nature comes with two isotopes, three isotopes. The third one is very minute, but two isotopes, 238, 235. 238 is 99.3%, and the other one is 0.7%. So 99.3, and the other one is 0.7. So this is why we will notice that the 238 is important in nuclear reaction, and we'll understand why it's important. 238 does not go in thermal fission. It only proceeds for the fast fission, and you need an energy, a threshold energy of couple of hundred kilo electron volts. So can you compare it? Couple of hundred kilo, 100,000 electron volts compared to 25 milli electron volt. So kilo electron volt, hundreds of kilo electron volt. This is 10 to the power of 5. The other one 10 to the power of -3. You have an 8 order of magnitude difference between both of them. And there is fertile material. So what's the fertile material? It's the material that we use it in order to produce a fissile material. So uranium-238, it's fissionable. So it can undergo fission, but it cannot sustain the fission. And also it's a fertile. Why? Because if I bombard the 238 with a neutron, what will happen is it will transform to plutonium-239. So I will stop here and continue next time.